So we want to take a look at an integration technique called trig substitutions. These will be integrals that somehow involve an a squared plus b squared, or maybe an a squared minus b squared. And either the a or the b might have the variable of your integration in it. It's going to turn out that by using trig functions, we'll be able to manipulate these integrals into very different looking integrals, but ones that we'll be able to actually integrate. The thing is, there are three identities here from trig. They're all the variations of Pythagorean relationships. The one that people are most used to is sine squared plus cosine squared equals 1, but if I rearrange that a little bit, I have 1 minus the sine squared of theta is the cosine squared theta. Likewise, 1 plus the tangent squared theta is the secant squared theta, and if you rearrange this one a little bit by subtracting the 1 over to the other side, you get that the secant squared theta minus 1 equals the tangent squared theta. Okay. Now, the thing that I want to point out, two things I want to point out about these. One is that each one is either a sum or a difference over here on the left-hand side, and it's a perfect square over on the right-hand side. That's kind of nice. The other thing is, one of these has a 1 minus the variable squared, one has the variable squared minus 1, and one has a plus sign with, well, with an addition, it doesn't matter what order they're in, but a constant and something with the variable in it. So depending on what I'm working on, I will decide which one of the three I want, depending on whether it looks most like this one or that one or this one. So let's do a first example of how a trig substitution works here. So I am going to do the integral of x cubed over the square root of 1 minus x squared dx. Okay, so first of all, I noticed that a u substitution is not going to work for me. Well, at least my first attempt at a u substitution, I look at this one and see 1 minus x squared on the square root. That's my first thought of, hey, this is what I should let u equal. But then I need a 2x dx, and I got an x cubed up there. It's possible I could make it work, but I think easier is to say, well, now that I have this option, or I'm teaching you this option, I've got this 1 minus x squared. And I look up here at these three things, and I think that that 1 minus x squared looks most like that this 1 minus x squared, I want it to be 1 minus sine squared theta. I'm not choosing this one or that one because this has got a plus in between. And this one has the 1 second and the trig function first. These two I think look pretty close to the same, and I make them exactly the same if I could get x squared to equal sine theta. If I could write sine theta, that would be great. Sine squared theta. So x would have to equal sine theta. So that's the substitution I do. Let x equal sine theta. Well, if x is sine theta, then dx equals cosine theta d theta. Now, one warning here before I make the substitution is that unlike u substitutions, this is going to get more complicated before it gets simpler. At least it's going to look more complicated. With u substitutions, you're usually taking big pieces of the integral and turning them into u. Other big pieces turn into du. Well, in this one, you're taking x and you're making it something more complicated, sine theta. You're taking dx, making it more complicated, cosine theta d theta. So initially, this integral is going to look more complicated. But we have a plan as to how it's going to become less complicated, and you'll see. So on the numerator here, I've got sine cubed theta. In the denominator, I've got a square root of 1 minus sine squared theta. And then I've got dx, which is cosine theta d theta. Right? It looks more complicated. It was this integral, now it's bigger. However, this was done with a purpose. That stuff underneath the square root, the square root of 1 minus x squared. I was saying, hey, that looks like a 1 minus sine squared theta. And actually, now I have it written here, it is 1 minus sine squared theta. But 1 minus sine squared theta, oops, sorry, I keep sliding up and down. 1 minus sine squared theta is cosine squared theta. So the stuff under that square root there, I'm going to replace by, so I've got a sine cubed theta, I've got a square root of cosine squared theta, and then I've got a cos theta d theta here. This is nice, where I cannot distribute the square root over that difference. I know a lot of people try it. It doesn't work. I can take the square root of cosine squared theta and get cosine theta. So that denominator, sine cubed theta over cosine theta, that denominator is just cosine theta, and then I'm multiplying by cosine theta d theta. And the cosine thetas cancel out, leaving me now just the integral of sine cubed theta d theta. Okay. Initially, it looks more complicated. At this stage right here, this definitely looks more complicated than what I started with. But we made the substitution with a particular thing in mind, and then that thing simplified, and in this case it actually canceled out as well, to get this. Now this is very much like out of section 7.2. The way I would do this is I would write this as sine squared theta times sine theta. I would substitute sine squared theta as 1 minus cosine squared theta. And then I do a u substitution with u equal cosine theta. Du is minus sine theta d theta. And this looks like the minus sign comes in. So minus the integral of 1 minus u squared du, which is negative u plus u cubed over 3 plus a constant. Working our way back now, u was cosine theta. So I've got minus cosine theta plus cosine cubed theta over 3 plus a constant. But I'm not all the way back yet, because somewhere way back up here, let's scroll back, this didn't start as thetas, this started as x's. So there's this relationship here, this substitution that we did. I'm going to write it down again down below here. We had that substitution of x, I need some place to put this here, of x equals sine theta. That was the substitution we did. Somehow I got to figure out what cosine theta is. Well, there's a couple ways that I do this. One is I'll draw a triangle. Heck, it's trig. There's always a triangle involved here. If this is the angle theta, I want the sine of theta to equal x, and I'm thinking of this as x divided by 1. So if I make this opposite side x and the hypotenuse 1 of this right triangle, then I've got a triangle here where the relationship between x and theta is the same as my equation there. Take the sine of theta, you get x divided by 1. So x is the sine of theta. This also then allows me to calculate this other side using the Pythagorean Theorem. The hypotenuse squared minus that thing squared, so 1 minus x squared is the length of that side. I want to point out that I feel good about that because that square root is exactly the square root that I started with in my integral way the heck up here, right, that I was trying to work with to start with. So when that happens, I figure I'm on the right track. So anyway, this triangle lets me see now what cosine of theta is, because cosine of theta is the adjacent over the hypotenuse. So looking at this thing, the cosine of theta is the square root of 1 minus x squared over 1 plus cosine of theta, square root of 1 minus x squared over 1, but I need that cubed over 3 plus a constant. Square root of 1 minus x squared plus, you can either write it that way or you can write it as 1 minus x squared to the 3/2 power times a third plus c. Okay. Let's do another example. Let's do this one. Let's do the integral of x squared over 1 plus x squared. Now this one actually has several ways it could be done. In section 7.4 we'll have another method for doing this. But for now, I'm looking at this thing, seeing that 1 plus x squared. That 1 plus x squared, I'm going to scroll all the way back up to the top here. 1 plus x squared looks not like the one we use. It's not 1 minus sine squared x. It looks more like this one, 1 plus tangent squared theta. So I'm looking at that I'm looking at that 1 plus x squared and saying, hey, I want that to be 1 plus tangent squared theta. So x has got to equal tangent theta, and that's my substitution. Right? Each time I do one of these trig substitutions, I'm trying to match one of those three identities. Either 1 minus something, 1 plus something, or something minus 1. Okay? And in this case, it's a 1 plus something. So x equals tangent theta, dx equals secant squared theta d theta. Substituting in here now, the x in the numerator there is tangent theta, so I've got a tangent squared theta on the top. I've got a 1 plus tangent squared theta on the bottom, and then the dx turns into a secant squared theta d theta. And, again, I've picked my example appropriately here for nice stuff to happen. There's a tangent squared theta on the top. The 1 plus the tangent squared theta, the whole point of choosing the 1 plus tangent squared is that's equal to secant squared theta. Right? We chose the tangent to make this look nice. 1 plus the tangent squared theta is the secant squared theta. And then multiplying by the secant squared theta d theta. That was the dx, right? That came in from there. Secant squareds cancel out. And I'm just looking at the integral of the tangent squared theta d theta. And again, this harkens back to the previous section of how do you integrate something like that. Well, with tangent squared, I'd probably convert it to secant squared theta minus 1 because I can integrate that. The integral of secant squared theta is tangent theta, and then the minus 1 integrates to minus theta, okay, plus a constant. I now have to work my way back. Remember, my substitution was x equals tan theta. So actually, this one's kind of nice because that tan theta is just an x. And the theta is, well, if x is the tangent theta, then then theta equals the inverse tangent of x, right? Take the inverse tangent of both sides. And remember, that's not 1 over the tangent theta, that's the arc tangent. So anyway, that's what I want, the arctan of x plus a constant. Okay. We will do some more examples with some maybe some trickier numbers involved, but the basic thing in each one of these trig substitutions is you're trying to match either 1 minus sine squared theta, 1 plus cosine squared theta, no, 1 plus tangent squared theta, sorry, or secant squared theta minus 1. Any one of those three can be converted into a perfect square. So we'll do some more in the next video.